In this video, we will be dealing with the NCERT textbook exercises. So let's start. The first question, calculate the molecular mass of water, carbon dioxide and methane. So let's start with water. Okay. To calculate the molecular mass, we need to add the individual atomic masses of the elements. So here it will be 2 into the atomic mass of hydrogen plus the atomic mass of oxygen. So 2 into 1.008 U plus 16.00 U, because there's only one atom of oxygen. So when we simplify this, we get the answer as 18.016 U. The next question or the next bit, CO2, that's carbon dioxide. So similarly, you have molecular mass of carbon dioxide will be equal to the molecular mass of carbon plus 2 into the molecular mass of oxygen, because there are 2 atoms of oxygen. And when this is simplified, we get a value of 44.01 U, because the individual atomic masses are in U or AMU. This is, if you remember, we studied about this in the atomic and molecular masses. And the third one is methane. So molecular mass of methane equals to the molecular mass of carbon plus 4 into the molecular mass of hydrogen, which is equal to 16.042 U. The individual atomic masses are taken, the units are taken as U, and so the final molecular mass also has the unit U. The second question, calculate the mass percent of different elements present in sodium sulfate. So the formula of sodium sulfate is Na2SO4. So the mass percentage of each element in sodium sulfate is the mass of that particular element divided by the molar mass of that element, of that compound. Or let me just put it this way. Suppose we need to find the mass percentage of sodium in this compound. The mass percent will be equal to the mass of the element, in this case it's sodium, divided by the molar mass of that compound. So here it's Na2SO4 into 100. So here we need to figure out the molar mass of the compound. First let's calculate the molar mass or the molecular mass basically. So molar mass of Na2SO4 will be equal to 2 into the atomic mass of sodium, that's 23.0, plus atomic mass of sulfur, which is 32, plus 4 into the atomic mass of oxygen, because this compound has 2 atoms of sodium. So this is sodium and 1 atom of sulfur and 4 atoms of oxygen. Okay, so when this is simplified and basically when we add all of this, we get the molar mass equal to 142. Now to calculate the mass percentage, all we have to do is divide the individual mass by the molar mass and multiply this value into 100. So mass percentage of sodium will be equal to 23.0 divided by 142, and because there are two sodium atoms in one molecule, this will be multiplied into 2. The whole thing is multiplied into 100, and when this is simplified, we get the value of 32.39%. Next is the mass of sulfur, mass percentage of sulfur, which is, here you have just 32 because it's only one atom of sulfur, and we divide it by 142, which is the molar mass of Na2SO4, and into 100 because it's a percentage, and this comes up to approximately 22.53%. The third is mass of oxygen. So mass percentage of oxygen. So here there are 4 atoms of oxygen in one molecule of Na2SO4. So 4 into 16.00 divided by 142 into 100, and when this is simplified, we get 45.07%. So we just had to calculate the mass percentage. The mass percentage is calculated by dividing the mass of that particular element in the compound divided by 142, divided by its molar mass. So because there are 2 atoms of sodium in this compound, it is multiplied by 2 over here, the mass is multiplied by 2, and there are 4 atoms of oxygen, the mass of oxygen is multiplied by 4, and because there's only one atom of sulfur, there is no multiplication happening over here. Question 3. Determine the empirical formula of an oxide of iron which has 69.9% of iron and 30.1% of dioxygen by mass. We've been given the atomic masses of these two elements. So let's start. So you have two elements, that is iron and oxygen. Next, we have its percentage composition. We had already dealt with such kinds of problems in percentage composition. In empirical and molecular formula. So percentage composition is given as 69.9% for iron and 30.1% dioxygen, which is oxygen. Next, we've been given that the atomic masses of these respective elements are 55.85 AMU and 16.00 AMU. Next, we need to find out the moles of atoms. So that will be done by dividing the percentage composition by the atomic masses. So 69.9 divided by 55.85 and 30.1 divided by 16.00. So this will give us 1.251, but since we have only 2 decimal points, we'll be rounding it off to 1.25, and when we divide these two values, we get 1.88. Now we've calculated the number of moles of atoms which are present. Next, we need to find out the mole ratio, and this is done by dividing both of these by the smallest value. So 1.25 divided by 1.25 and 1.88 divided by 1.25. This will give us 1, but this on the other hand will give us 1.50. So the mole ratio over here is not a simple whole number ratio. So we need to convert it into a simple whole number. And this is possible when we multiply this value into 2. So we will be multiplying both these values with 2 and we'll get 2 over here and a 3 over here. So then we will have to simply write the empirical formula. Empirical formula equals to Fe2O3. Now, this is the third question. In the eighth question, the same compound has been given, but here we've also been given the molecular mass. So first let's write down the empirical formula mass. We have to find out the empirical formula mass, which will be equal to 2 into the mass of iron, that is 55.85, plus 3 into the mass of oxygen. So when we simplify this, we will get a value of 159.7 grams per mole. We have been given the molecular mass or the molecular mass that is equals to 159.8 grams per mole. So the value of N equals to the molecular formula mass divided by the empirical formula. So 159.8 grams per mole divided by 159.7 grams per mole. So we can cancel these two because they're the same value and we get approximately 0.999, which is equal to 1. This means if N equals to 1, this means that the empirical formula is the same as the molecular formula. For the detailed explanation about this entire process, do check out the video of empirical formula and molecular formula. Question number 4. Calculate the amount of carbon dioxide that will be produced when we've been given 3 different conditions, and yes, this question is based on stoichiometry. So first, let's figure out what the equation is. Okay, so the basic equation is carbon is a solid. It is burning in the presence of oxygen. We all know combustion has to take place in the presence of oxygen to give rise to CO2, which is also a gas. First, let's see if this equation is balanced. 1 carbon atom, 1 carbon atom. 2 oxygen atoms, 2 oxygen atoms. So it's a balanced chemical equation. And in a balanced chemical equation, we know you get a lot of information right from the number of moles to a number of molecules and even the masses. So 1 mole of carbon reacts with 1 mole of oxygen to form 1 mole of carbon dioxide. Not only that, since we have 16 grams as a part of our question over here, let's also write down the masses. So if there's going to be only 1 mole, which means there's 12 grams of carbon reacts with O2. O2's mass would be 16 into 2, which is 32 grams to give us 44 grams of carbon dioxide. Now if you see, this is also follow the law of conservation of mass. So the first question, 1 mole of carbon is burnt in air. So we need to find out how much of carbon dioxide is being formed. So if 1 mole of carbon is burnt, automatically 1 mole of carbon dioxide is formed. So 1 mole of carbon dioxide corresponds to how many grams? 44 grams. So the answer is 44. Let me repeat it again. Here we have 1 mole of carbon dioxide forming, 1 mole of carbon reacting with 1 mole of oxygen to form 1 mole of carbon dioxide. So 1 mole of carbon is burnt in the air, which means it has any amount of oxygen. Then 1 mole of carbon dioxide is formed, whose mass or whose amount or quantity would be 44 grams. Next, 1 mole of carbon dioxide is burnt in 16 grams of dioxygen. Here you have 32, which means 32 grams of oxygen. But in our question, in the condition, reaction conditions, the amount of oxygen which is available is just 16 grams, which means it's only 0.5 moles of oxygen is present, which means 0.5 mole of carbon. Okay, instead of writing it like that, let's just put it this way. C plus O2 gives rise to CO2. In our original case, you had 32 grams, but in our under this question, it is 16 grams. If it is 16 grams, then it is half of the mass which is present over here, which means the number of moles automatically becomes 0.5. So you have only 0.5 moles is the amount of oxygen which is present, right? So this is so even if you have 1 mole of carbon in the atmosphere, or in our reaction, when it reacts with only 0.5 mole, there'll be an excess of 0.5 mole of carbon left. This is from limiting reagent as our topic. So here oxygen is acting as the limiting reagent because it gets completely used up in the chemical reaction, and this leads to the formation of only 0.5 moles of carbon dioxide. So this will also be divided by 2, so it will form 22 grams of carbon dioxide, because in this condition you only have 16 grams of oxygen. The next one, here they've given us 2 moles of carbon is being burnt in 16 grams of oxygen. Now when we studied about limiting reagent, we learned that no matter how much the excess quantity of one of the reactants is, once this reactant gets used up, the reaction will stop. So because of that, the amount of carbon dioxide formed is 22 grams or 0.5 moles. Because oxygen is acting as the limiting reagent. So even if I have 100 moles of carbon, if I have only 16 grams of oxygen, then the amount of carbon dioxide that will be formed is 22 grams, okay, or 0.5 mole. Okay, so in this question we studied, this question is mainly based on stoichiometry and the concept of limiting reagent.